Okay, so welcome everyone. Uh, check, the recording. Yeah. So welcome to our last lecture or lecture 10. So here we will learn about how we can uh, do numerical integration for stochastic differential equation. So what is the stochastic differential equation? So let us consider, so since any order of differential equation, we can write down as first order differential equation. So, nth order is equivalent to n first order, which we have gone through a lot of times in this course. So, let us learn first understand how you can solve a first order differential equation which has a deterministic part and a stochastic part. So, for example, this is let us consider a differential equation which looks like this. So, we have q xt and we have g xt psi t. So, this is a general form of the differential equation. So, where this q and g, what are these? So, these are differentiable function. So, these are differentiable and also these are analytic. That means these are analytic functions, so you can do ordinary differential, you can apply ordinary differential calculus to q and g, but here you have another term where you have this chi. So this is basically where their stochasticity comes into system. So let us consider, so it is a noise term. So it can be of different kind of noise terms. So it can be Gaussian noise or it can be colored noise. So there exist different kinds of noise and so on. But so what we will mainly focus on is on Gaussian noise. So why Gaussian? So let me motivate you because there are lots of physical processes exist in the nature which has this kind of noise term. So for example, we have heard of this Brownian motion, and also suppose your system is at room temperature, so there is collision of air molecules with your system. So due to this reason, so so there are so in Brownian motion, the noise that you guys have. So what is Brownian motion? So suppose you put you suppose there is water, and in water, so you have fallen some object, and so its dimension is very small. So if you look at its motion very carefully, so it will perform some jittery kind of motion. So that is basically a Brownian kind of motion. And also you have, so for example, suppose if the system that you are experimenting with, so that you have kept in room temperature, so that is not under, and also that is not under perfect vacuum. So there is air present which is interacting in a system. So there will effectively there will be collision of air molecules with the system, and so since the system is at non-zero temperature and finite vacuum, so almost in all the physical processes that you daily encounter with, so they inherently come with some noise term. So that is why it is important to know how you can tackle this first order. So how you can tackle this differential equation which is noise. And the most common type of noise, so I mean that we encounter is mainly Gaussian, and there can also be other kind of noise, so colored noise. So generally, the Gaussian noise means, so if you look at the response in frequency, so I mean so for example, so if you look in the frequency domain, so this Gaussian noise generally doesn't have any peak there. So I mean, for example, you can add noise to your system. I mean, external noise you can add. So I mean, in experiments, function generator have this type of noise. So and you can look at in the I mean spectrum analyzer, and you can check for what is the noise profile. So if you look at in the spectrum analyzer, so mainly for Gaussian noise, so you will observe this flat kind of band. And for colored noise, so colored basically means it has particular frequency. If you look at the frequency domain, so maybe at particular frequency you will have, I mean, larger amplitude. So that is why it is called the colored noise. So these are the basic type. So for now we will focus on the Gaussian noise, and this noise. So this this noise. So let me write down this equation here again. So dx dt is q of xt, then we have g of xt, and we have xi t. So this gxt, I mean, it can be a constant or it can be a function of x and t. I mean, so for example, let us consider these two cases. Gx is c. So this is one case, and there can be other case where gxt. So for example, suppose the simplest one. So suppose this is x. So it can be very complicated, but for now, let us suppose it to be x. So how does the equation look like in each of the cases? So for the first one, we have our equation of this kind. So dx dt, which is q of xt, then we have constant term into xi t, and here we have dx dt, which is q of xt plus x chi t. So here what you are seeing, so what is the difference between these two? So here effectively the noise term is being added to the equation as a force term, but here I mean this noise term is being multiplied with the displacement, and then it is adding as a force term. So I mean this depends on the path of the system. So for example, this is its initial displacement, so it will have, so for example we have a noise term. So yeah, I mean this noise, you can think of it as a random number. So I mean it has a random value, and so due to this, and this is not analytic. So this xi t is not differentiable and not analytic. So this xi t, so that we are concerned about. So for example, it has a random value, and this is the initial x0. So due to this xi 0, you will have a certain x value. So I mean it will from this equation, let suppose after a time step it has x0 to this x value is here, x1. Now what will happen? So this x1 will be multiplied, so I mean multiplied with the random number, and then it will be updated. So that is why here the noise term, it depends on the state of the system. So I mean it depends on the current state here, intermediate step. But here if you look at it, so it is not being multiplied with x, it is directly being added to the system. So here the stochastic term doesn't depend on the system parameter, but it here the stochastic term, or it depends on the intermediate steps of the system. So here stochastic term does not depend on the state of the system and parameters of the system. It is directly being added to the differential equation. Okay, but if we look here, so here this stochastic term, so it depends on the intermediate step, depends on the intermediate state of the system, and I mean it can also depend on the parameters of the system. So it is being multiplied with system state and then being added as a forcing term to the differential equation. So that is the main. So that is the difference. That is the difference if we have a constant term and if we have a term. I mean, which depends on this system parameter. So this case is known as additive noise because it is directly being added to the system, and this case is being known as multiplicative noise. So because here the noise term is being multiplied with the state of the system and then being added to the and then being acting as a forcing term, but here it is directly being acting as a forcing term without affecting the intermediate steps. So so there is explicit dependence and there is no explicit dependence. So that is why this is I mean called additive and multiplicative. And I mean so in multiplicative, so since it depends on the system state, so it I mean it so there is two choice. So you can at what time you will take this side. So I mean since I mean if we have an analytic function, so in that case you can consider the system. So I mean so since I mean so whenever you are doing this Euler method, so I mean you have so basically you evaluate this q. So at each step, so you so in the explicit method, so you evaluate at t equal to t, then with this value of t equal to t, you will evaluate at t plus delta t. So that is Euler implicit, and in Euler implicit, so what you do, and in RK force, for example, so you evaluate at the midpoint. So here also you can do the evaluation at the midpoint, or also you can so noise time you can add at midpoint or on the in or or the at the initial. But here since this is not analytic, so I mean these two approach give different result. So this is I mean and it depends on your system which type of calculus you want to use. So here we have two different kind of calculus depending on on that. So one is Ito and another one is Stratnovich. So we will not go into too much details into the multiplicative case because I mean that will be a very I mean so that is also so area of current research. I mean you and you have to, by knowing your system, you have to so first you have to know how what type of noise is being added to a system. So is it multiplicative or is it additive? Then you have to figure out what type of calculus you should use. So Ito or Statovich. Basically in Statovich it evaluates at the midpoint, and here it evaluates at the initial, at the starting point. So if you are going from t to t plus delta t, so in Ito you will be evaluating here, and in Statovich you will be evaluating at something like dt by 2. So what do you, what you used to do in Euler or RK2? But here the issue is that the noise term is not analytic. So these two calculus so give widely different result, and it's up to your system. So so what type of e-calculus you can use. But in additive noise, so since here what happens, so basically it doesn't depend on the state of the system intermediate step. So here Ito and Statovich so both give similar result. So we will focus mainly on this additive noise now. And since this Ito at Sasnovich board gives similar result, so we will not go into too much details of them. So basically, we will first formulate how the numerical method to solve this kind of equation. So dx dt, here we have this q of xt, then g of xt, and xi at. So we will this will be a constant term, and if it is a constant, then we will figure out what is the update rule. So for example, if you have we know this update rule for Euler. So this is basically plus dt into the function evaluated at xt yt xt at t. So if g is 0, so then this is a simple equation. So this will be evaluated at x at t. So this is the update rule from going t to t plus delta t that we know from Euler method. So this is Euler, and there are improved methods. So RK2, RK4. So these are the different kind of method available. So when g is 0, so this is valid when this g is 0. But when this g is non-zero, and so the simplest case will assume that is a constant, then we want to know what will be the update rule. So let us try to proceed with that. So now this xi t is a Gaussian white noise. So it has mean. So what does this Gaussian white noise mean? So if the mean value of it will be 0, and this noise, so basically what does noise mean? So basically if you look at the value of this xi at a certain time, and you are looking after, so for example this is at t1, then you are looking what is the value of xi at t2. So this is suppose at t2, then you have at t3, then at maybe t4, then at t5, and so on. So so with increasing time, so you are suppose looking at the xi value. Now this values, if it is a Gaussian noise, so that will be delta correlated. So what does this mean? So this point and this point, there doesn't have any correlation if the time differs slightly. So that mathematically we can write as psi t1 psi t2. So correlation is delta correlated. So if t1 minus t2 is 0, so it effectively means t1 is equal to t2. So in that case, this will give us a non-zero value. And if t1 t2 T1 T2, I mean this is non-zero, so in that case this is zero correlation. So these are the properties of this so this is the property of this Gaussian noise. So I mean the mean value. So if you generate this random number for a large enough sequence and look at the mean value, then it then the mean value should be zero. And also if you want to look at the correlation, then that correlation is will be delta correlated. So that means if you are looking at correlation of the point which if the both points are generated at the same time, so obviously in that case it will have non-zero correlation. But if you differ slightly, very slightly, T1 minus T2 can be suppose epsilon, which is almost close to zero. But even if it varies very slightly, in that case you will have zero correlation. So that is the definition of this Gaussian white noise. And why it is called white? So because since this is in time, so you can think intuitively in time axis it is delta correlated. So what is the frequency response of a signal which it is delta correlated in time? So this is like so if you look at the response, so it will be like this. So this is delta correlated in time. So if you want to look at what will be its Fourier spectrum, so it's Fourier transformation of delta function. So this is your time axis and this is your, and let us say, correlation. So in frequency domain it will look like it will have a flat kind of spectrum. So that the Fourier transform of any delta function is a flat spectrum. So that means there is no specific all the frequency components are present in a system. So that is why it is effectively uh, so it is so that is why it is called white. So white means combination of all the frequency. So here one thing you can check. So there is a task. So you can generate this rand n. So there is this rand n function in MATLAB which produces the random number between, so or so we can proceed with the rand function only, that will also be good over there. So this rand function, so it produces between 0 to 1. Okay, so rand n is good. So rand n, so this, if you try to look at the function, then try to generate this random number for a certain step. So for example, generate 1000 of this random number, then try to look at their uh, mean value. So first look at the mean value, then what you can do. So suppose you are generating 1000 number and this is generated for t equal to 1 to 1000. So for each of this time, so generate a random number. So you will have a series of this xi as a function of t. Then you can use the FFT to transform frequency domain, and then you can look how the FFT signal looks like. So it should give you a flat kind of spectrum. So that basically tells you that it is delta correlated in time, and it has if you look at the xi value, mean value, so it will be 0. So which are the properties of the Gaussian white noise? So so that is why when you are working in MATLAB, so you can proceed with this random function. Okay. Uh, So now let us come back to our original equation, which is dx dt equal to q xt g of xt chi t. Now after, so how we can solve this? So after a discrete, so I mean, let me just briefly go through it. I will not go into too much detail. So I mean, how we can express the value of x after a time interval h. So we can write, from this we can write x at t plus h will be equal to x at t plus this will be from t to t plus h, and here we will have q x s. So and since we are integrating with t, so I will just replace t with s. So this is our, this will be ds, and here you will have t plus h g x s s xi s ds. So now if you, I mean, so if you use Taylor series expansion, of function qxt and gxt, then from this equation you will end up with this. So I mean, you can just try to prove it, but I mean, just let me write it down. So it is xh plus h q xt, then we have q prime, which is the derivative of q, then we have here xt t, and there is this integration term t plus h x at s minus x at t ds. Then we will have here w h t g x t t, and we have plus g prime x t t. So here we will have the integration from t plus h. Let me write it down, x s minus x t psi s ds, and here we have h plus t usually multiplied, so with order of x s minus x t squared. So squared, okay. So where, so what is this omega h t? So it is written as t t plus h xi s ds. So you can check this, I mean, you can try to prove it. So but this is, I mean, how the x plus x at t plus h will evolve. So now I mean, if we incorporate the properties of this Gaussian noise, then I mean, one can write this omega h t to be root under h into ut. So where this h is the time step, which you know. So this is time step, and what is this ut? So ut is a set of independent Gaussian random variable with zero mean and variance 1. So it has variance 1 and it has mean 0, and this is, I mean, a random variable, set of independent random variable. Now So for example, suppose so we want to know what is the equivalent of Euler method. So for Euler method, so what we have to do, we have to consider all the terms which is up to the first order of h. So we have to consider all the terms up to the first order of h. So if we so now if I look at the equation, so if we look at the third term, so this is order of h square. So this is order of h square. So you can try to look at it, and so and since this omega h, so this is this scales as root under h. So I mean we need to evaluate the integral of the fourth term. So if I now I mean so here you can use the Stathnovich. So I mean you can use both Stathnovich and Ito. So it doesn't depend for additive noise. But since we are still dealing with here Q, I mean Q G is our X T. So let us proceed with the Stathnovich calculus, and the so from Stathnovich calculus we will get this G X T and its derivative, and from t to t plus h we have x minus xt xi s ds. So this we will get if we use the certificate calculus will be half g prime. So g prime is the derivative evaluated at x comma xt t. Then we have g which is x at t and t. Then we have omega square h t, and we have term of the order of h to the power 3 by 2. So now the equation, so from so if you use this, then our original equation, or so from here, so using this we can write x at t plus h will be x at t plus h q evaluated at xt t. So this is, I mean, the traditional Euler, and here we have another term added which is g x t t root under h ut, and here we have h by 2, and here we will have g x at t. Then we have this is value, this will be t here, and g prime which is x at t comma t, and then we will have u square t. So this is known as Milstein algorithm. So now what will happen if you have additive noise? So if you have additive noise, then this g prime, so this term, I mean this will be 0, because if you, so for additive one, this is a constant, so its derivative will give us 0. So that is why, I mean, it is not important if you are using Ito or Chernovich, because anyway this term will be go to 0 if you have this constant term. So that is why, I mean, for additive noise both gives you same result, and if you have the second term, this term to be 0, So that it basically means this will be 0 for additive noise. And if this is 0, then our equation will look like this: x at t plus h, which will be x at t plus h q at x t t, and plus we will have, so let us call this constant to be d. So if we call it d, so then we have root under h into ut. So I mean this is a constant which represents the additive noise strength. So this is the ultimate update rule for first order ODE and for system with additive noise up to order H. So and this is generally known as Euler-Maruyama algorithm. So what is Euler-Maruyama algorithm? So if we have, I mean, if we have a first order differential equation and we are considering only the noise to be additive, then if we use the equivalent of Euler method, I mean in ordinary differential equation process we have the Euler method. Now I mean, so in case of system with noise, so Gaussian noise or random noise, so which is effectively white noise, then our equivalent method is Euler-Maruyama algorithm. So and this is the corresponding update rule. So let me write down this. Let me finalize. Write down a summary of this. So our system. So let us consider our system equation is like this. So mu. So we can have. I mean. So this function. So let us for now consider a simple function dt and sigma d omega t. So we are consider. So this q we have considered a very simple function. So which is x, and this is our mu, and this is our sigma, so and this is our noise strength. So this is the, I mean, drift rate, and this is the amplitude for additive noise, which we are considering as additive noise strength, and this is the Wiener increment. So I mean it is delta correlated in time. So I mean since it is, so what will be, so d omega should be 0, and if we calculate the standard deviation, so it should be a dt. So and what is the update rule for this? So update rule for this will be x at n plus 1, which will be xn plus mu xn delta t. So this is the Euler part, and then we have the sigma delta omega n. So where what is this delta omega n? So it is basically root under delta t, because we know that it depends, I mean it scales as root under h. So it will have this root under delta t, and you will have this xi, so which we will draw from this xi n, you will draw from 0 to 1. So this is the update rule which we will use, and this is the equation first which we will try to solve. Okay, so uh, let we can wait for, let me take a break for 2 minutes, and after that I will solve this equation in MATLAB to show you the difference between the, I mean, deterministic equation and with the stochastic equation. then since you can write this as a vector form, so and also since any order equation can be decomposed into n first order equation, then after that we will I will show you how you can use this method, or you can use this formula in case of harmonic oscillator. So so let me take a little quick break, and after that we'll start with the MATLAB coding. Okay, so let me show you the equation which I will try to simulate. Okay, so this is the equation. So this is if we don't have this term, so let us look at just the deterministic part, which is xn plus mu xn delta t. So this is just this solution. What is the solution? So this is something like e to the power mu t, because for that the differential equation will look like dx dt will be equal to mu x. And if you want to solve it, so basically it will give you xn plus 1 will be xn plus mu xn delta t. So which is consistent with the equation. So your solution will probably should look something like this. So if you solve the Euler method, deterministic part should give you, if you have mu to be negative, so mu negative, your solution will look like this. And if your mu is positive, then maybe your solution will look something like this. So let us look at what will be the solution look like if we have a noise term also in the system. So let me show you that. First, let me write down this here all, close all. Let me save it. Save as lecture 10, and it is um, constant stochastic. So okay, so now let me first define the parameters. So we have mu, so let us call mu, and let us set to be 0.5 for now. Then we have sigma, which is basically the additive noise strength. So for now, let set it to 0. So this is additive noise strength, and this mu, I can call this as drift rate or the damping. So if mu is negative, so just for now call it drift rate. And we have here sigma, which is basically the additive noise strength. And what we need, so if we want to solve, or and what is the condition that we need? So we know mu, we know what is our sigma is, and we need an initial condition also. So let us take the initial condition. So call it x0, and let us take it to be 1. So this is our initial state. Fine. Now what we need, so we need the time step, and the time array we need. So let us take the final time to be maybe around 10. So this is total time, or you can call it final time. Then we have total number of steps, so let us take to be 5000 steps to be there. And so what will be dt? It will be basically the final time divided by number. So this is time step, and then we can create the array. So basically for creating the array, we will start from 0, and we have the times division to be dt, and we want to go up to t. So let me run it once, and you can You can see that this time array has been created here. So these are time array. Fine. Now what we want to do? So we want to solve and store the x values. So we can create array. So what will be the size of the array? So for example x. So it will be zeros. You will have 1 and you will have length of t. So what we will do in the program? So we will do independently for Euler and Euler Maruyama, and we will compare them. So maybe we need two arrays. So x we can write here Euler. So we will store the values that we will get by solving the Euler method and store in this array. And let us have another array which is x em. So the values that we will get by solving the Euler Maruyama algorithm, that we will store here. So this will be of same size also. So let me just copy paste it. Okay, so let me write down here. So values using Euler algorithm will be stored here. And what do you want to store here? So values using Euler Maruyama algorithm will be stored here. So, okay, so we're set with the all set with the arrays. Now what do you want to do? We want to write down the update loop. So we have to run the loop for the time array. So for uh, I equal to I equal to 1 to length of t minus 1. So what will be the update rule? So and also we need this term also. So this root and so this omega n, which is delta t into xi, and this xi we have to take a random number. So let me write down what this xi will be. So let us call it to be d capital omega, and this will be so square root of dt, and that will be multiplied with a rand n. So because we want the mean value to be 0 and variance to be 1. So that is why you have to use this rand n function. So it will give us square root. So let me just show you our output here. Okay, so let me try to let me show you that this random n has a 0 mean. So let us 1 to 2000. So let me create an array. See zeros 1 to number. So let me define a number which is into the 20,000, and we are creating an arrow of this length, and here I will run a loop and generate this random numbers and store in this array. So C1 I, so we will store here and we will end it, and let me write down C here and let me run it once. Okay, so here we have to put this down. Okay, so now if I look at the C array, so this is our array, and you can see that, and we can try to check what is the mean of C. So let me check mean of C. Now increase it more. So you can see that if we increase, if we increase the number of elements, then its mean value is almost going to 0. So if I decrease the number of elements, then you can see that it is finite. So if I more decrease it, so it's now almost finite. So if I do it for 20 elements, so now it is in the first order, so 0.01 or 0.09 something. But if you increase the number of points, so here you can see that it is almost 0. So that is why we are using this rand n function. Okay, so once we got this t omega array, so after that we will use the Euler-Maruyama and Euler method. So first let me show you the output for Euler method, and for Euler method what will be the output? So this is your array which you will update. So here you will have to write 1 and I plus 1, which will be xu1I, and with that you will add so you will add what? So you will add mu, and here you will have this xui1, and with that you have to multiply the dt. So this is your Euler method, and next you will have Euler Maruyama method. So if you plot the output here, so you have to write the update tool for Maruyama also. So this is Euler Maruyama. So and so this term here you will have m. So Maruyama this, and there will be another term also. So which is basically sigma, and that will be multiplied with d of capital omega. So and you will end it. So now let me run this. You can see that the values have been stored. So Euler Maruyama. Where to call the zero. Okay, so you have to pass the initial value. Yeah, so that is why if you are starting from 0, so it will be 0. So this x u and the first value, that will be x0 and x u, so m, the first one, so 1 1 1 1, that should be x0, and we have here xn. So let me run it. Okay, so now you can see that values have been updated, and this is xu. Fine. So now let us try to plot both of them. Okay, so one thing I will show you. So if I make it non-zero, and if I uh, make this, so okay, let me make it 0, and let me make this x0 to be 0. So now let me run it, and let us look at the array. This is 0, this is 0. Now if I make this sigma to be non-zero, and let us look at this xm. You can see that Euler method is giving us 0 value, but even if the initial condition is 0, due to the presence of this noise, so you can see that there is a response in the system. So Now we can try to plot them together. So if you want to plot if you want to plot two curves in a single figure, then you have to use the hold on. So first let me plot the t, and here we will have x, and let me have a line width of maybe 1.5. Then we will use the hold on, and then we can put some label. After hold on, so we want to plot the this one also. Okay, so this is our uh, Euler, and this will be our Euler Maruyama. So let me change the style here maybe. So here maybe I can introduce something like this, and so let me call it time. So in x-axis we have time, and in y-axis so let me call the system state. So y level, and let me run it. Okay, so this is the response of the system when there is initial condition is 0. This blue one we are getting from the Euler, and this red one is we are getting from the Euler Maruyama. So let me have the initial condition a little bit different. So let me also make the damping to be negative, and let us have an initial condition, and let us look at the system response. So yeah, this blue one now is how the deterministic part will look like, and here there is this red curve. It shows the Euler response. Now if you just run the code again, so you will see different response in the Euler Maruyama. So you can see that the curve is looking different because so noise so because you're dealing with noise now, so it is not an analytic function. So that is why in each run, in each ensemble, you will have different kind of response. So in each run, we are having a different response. Fine. Now suppose, so what you can do, so you can run this uh, code for multiple times, and you can try to take the average of it, and you can check that what is how the graph will change with increasing ensemble number. So let me try to write it down here. So what you want to do, so you want to do the same task repetitively for multiple times. So so let me define the ensemble. So ensemble number is basically how many times it will run. Ensemble, and we want to run an array. So for example, for k or j equal to 1 to ensemble. So and we have to end here. So let me have the, so and let me make it j. So what does this mean? So when this j is 1, so it will plot the fast response in first graph, first figure 1. Then it will have the j value 2, and it will plot this in figure 2. Similarly, then the j value will be 3, and it will plot in figure 3, and in the same way, and in this way it will go on. Okay, so now also I want to, since I want to have the mean, so I would have liked to store the values that we are getting from solving this equation. So this x eu and x em, these two matrices, so these two we want to store. So for that we can create another array where so let me create arrays of zeros, and instead of 1, so so this is of 1 length t, So what will be the row number now? Now I will have to write down here ensemble. So so for each ensemble it will store the values here. So if I run it, so let me show you. So let me run, let me just so you can see here that it has created this 10, so since the ensemble is 10, so there is 10 rows. So in first row you will store the response for first run, then in the second row you will store the response for the second run, and in this way you will store the response in all for all the all the runs. So similarly we can create an array for Maruyama also. So we will have here our Maruyama array, and how will so after evaluating this, so we will store so array, and here you will have this. So what is j? So maybe j, and then here you will have all. So you will so your so what does this mean? So so this is first. So when j is 1, this is first row and all column. So you are telling to store this array along the first row, and similarly you can store the em also. So em, and this will give us em. So let me run it and let me show you the output of this. Okay, so this is for one run. So you can see that we are getting different kind of response for different runs. So I have to suppress output somewhere. Yeah. Okay, so these are the responses for total 10 ensembles. So now suppose you want to look at the mean. So how we can do? So let me define an variable which is mean of xu array, and that we so for calculating mean you have to just write down mean. So xu array. Similarly, you will have another array which is xem. So since this uh, this eu is this is you are getting from the deterministic part, so that is why it will not change in each run. So if you look at this eu array, so you will see that this value is same. So let me look at this. So you can see it doesn't depend on the run number. So because this is coming from a deterministic part. But if you look at EU array, so you can see for each of the run, this number is different. So because you are considering a random number here, so and you are solving a stochastic differential equation, so that is why for each of the run, so your system will give different kind of response. So because this is not an analytic function. So now what you can do, so you can look at how the mean behavior is responding. So let me copy it, and so let me call it. So the here the figure will this j value is from 1 to ensemble. So you can call it ensemble plus 1. So it will be figure 11 for if ensemble is 10, and here you want to plot this. So in place of xeu you want to plot this, and in place of xem you want to plot this, and let me run it. Okay, so this is for one run, this is for different run. So this is for different and this is the average one. So if you look, so this curve is not changing. The blue one which is coming from the deterministic part, so that is not changing. So that is why the average one and each individual response is similar. But if you increase the ensemble number, so let me try to do it for 30, and let me just comment this, otherwise there will be 30 this kind of responses will be generated, and let me run it. So this is how the averaged one looks like. So you can increase the ensemble. So okay, so let me start from uh, 1. So let me look, so let us consider this is 1. Okay, for 1, so if you have only one array, so that mean will give you a scalar number, so that is why it is not plotting anything. So let me start from 2. So this is, if you have 2 run, and if I run it again, okay, so this is quite different. Now let me increase it. So in one run it is giving this here, and still different. So let me try to increase it further. Okay, so almost, so we can see that it is being smoothed out. So response is, okay, so there is not too much different now. Again, we can run it, and we can increase the ensemble number, so we can make it to 100, and we can look at the system response. Okay, so more smooth now. Okay, good. So if in this way, if I keep on increasing this, then you can see that, so you will have 200 ensemble where you will have this kind of fluctuating motion. So what you are doing, so you are just taking the average. So this, will give, so now you can run it again, and you can look at the system response. So now there is not too much significant change. So that is why, it is a good idea to take the ensemble average, so that, you can look at the what is the response of the system. So when you are working with a model, and which has this stochastic noise terms, so you can, mm, in this way you can check how much ensemble you should take, so that the system converges. So the response that you are seeing, so if the if the mean response for this ensemble is uh, I mean replicating or not. So in that way you can check that. So the and so if so since this mu is negative, so you can see that it is exponentially decaying. So which we have guessed from here. So this is exactly also your stochastic differential equation also on the mean scale. So it gives you a similar kind of response. But if you look at individual responses, then there is this fluctuations which you will observe. So so this is for a system which has only one first order differential equation. So next we'll try to implement this in case of a harmonic oscillator equation. So let me proceed to with that. Okay, so let me save it first. So let me show it as lecture 10 constant, and let me write it here, harmonic STO. Let me save it. Okay, so here we will compare the Euler and Euler Maruyama for damped harmonic oscillator. So how can we extend the idea to damped harmonic oscillator? So if we so if let me write, let me show you here. So if I have a if system with this type of equation, So for example, suppose this is our equation, which is x double dot plus 2 x dot plus omega square x equal to 0. Then we can decompose it in so we can have a state vector which will like this, and using this you can write down x dot as v and v dot as minus 2 psi omega 0 v minus omega naught square x. So this is our this is our f of x. So this is our functional form will look like, and we can write down this equation, this second order equation like this. So dx of capital X, which is the state vector, which is basically this f of x dt, and we will have this g d of omega t, where what is the f of x? So f of x is basically this array. So you have v, and here you have minus 2 xi omega naught v minus omega naught square x. And what is this g? So this g, so it will have a noise strength. So let for now let us consider that in displacement there is no noise term being added, and in velocity there is noise term being added. So we are considering the noise term in the velocity. Okay, so now let us try to solve this in MATLAB. So let me go to MATLAB. So let me first uh, okay. So let me define the parameters first. So what are the parameters? So we have omega 0. So let us assume it to be 2 pi, maybe 3, which is the natural frequency. Then we have the damping ratio, which is zeta. So let us take it to be 0.05. Then we have the noise strength sigma, which we will add in the velocity. So let us take it to be 0.2 for now. Then we have the initial condition, and since this is a second order equation, so we will have two initial conditions. So us let the initial displacement is 1, and initial velocity, let us take it to be 0. Then we have the time array, so total time. So let again take it to be 10. So because so okay, so this is 10, and let us take maybe 10,000 data points. So what will be dt? Dt will be basically your final time, which will be divided by n, and you will define the time array, which will be basically start from 0. Dt is the time step, and you will go up to t. So you will have your t array. So let me run it. So we have your t array here, and we have our initial vector here. So then we have to create the array. So displacement and velocity. So let me for Euler we will have this Euler. So what will be the its length? So it will be zeros. It will be 2. So 2, one is for velocity and one is for displacement, and we will have n plus 1 here, or we can write length of t. Then we will have x. So let me just call it Euler, and we will have Euler Maruyama. So let me write it as Euler Maruyama. So here we will store the initial conditions. So now we have to store the initial condition first. So for storing this Euler and along all the rows and in first column, so we will store the x0. Similarly, in Euler Maruyama also it save it. So let me write it, let me run it and check it. So you can see that okay, so the initial condition is being stored here and also initial condition is being stored here. Okay, fine. So then we need the time stepping loop. So let us write for n equal to y to n or 1 to generate length of t minus 1. So what will be, so first let us calculate what the deterministic part, which is x Euler, and what we will write here. So basically we will store along all the columns, all the rows, and we will have this to be in class 1. So here we will have Euler. So I mean we will try to write a function. So I mean we will write a function for Euler. So Euler step. Maybe we will give this a name as Euler step, and then we have to define what are the parameters. So these are the parameters. So you have, I mean, oscillator, and you will pass the Tn value. Okay, so let me write down the function first, so that will be easier. So let me write down the function. So function, uh, so output. So just let me call it as x next, and here you will have Euler step, and you will what will be the what should be you give. So you have to write. So for example, suppose we will write another function also where you will give the form of the oscillator. So let me write that function first. So function which maybe will give me tx, and so let us call it oscillator equation. Define it like this. So we will pass x, we will pass omega 0, and what are the things that we need to define the function? Mm, so we need zeta also. So zeta also needed, omega 0 zeta. So we will write here zeta, and then what we will do? So we will basically store uh, the first value as x, then we will store the second value as y, and then we will write down what is our dx, which is basically v, and we will compute, we write down what our dv is, which is basically minus 2 zeta, and that will be multiplied with omega naught, and that will be multiplied with v, and there will be minus omega naught square x, minus omega naught square, and that will be multiplied with x. So that will give you dv, and you want to store this in maybe dx, and what will be the, so you will store this dx and dv, fine, and you want to end it. So what this function will give, so basically here you are writing here what is your equation. So, I mean, if you have a complex equation, so you can update this accordingly. And I mean, so if you call this function, so it will basically give you what is your dx is. So that means your dx value and dv value. So that will give. So now here, I mean, so let me define the Euler function. So where you will call the function f. So here you will have f, then you will have t. You also need to give what is x, dt, omega o naught. Then we also need to define what is zeta, and then it will calculate your dx. So dx you will calculate by calling the function which you have defined earlier. So that will be f t comma x omega naught zeta, and you will so give this x next, which will be x plus dx, and that will be multiplied with dt. So this will be your value corresponding to the Euler method, and you will end here. And you will similarly you will write another function which will give you the Euler output of the Maruyama algorithm. So for that, what you have to write down here. So you need here another term. So let me call it em step, and this will give you some. Okay, so let me call it x next. So this is basically the output, and here you have to also define what is sigma. So let me pass the sigma also, and so what will be, so there will be another term which is d omega, and that is basically square root of dt, that will be multiplied with this rand n. And how you will store, and g will be your, so I mean you don't want to add any noise in displacement, so you write 0, and you will want to, this sigma will be strength in your velocity. So here you will write this sigma, and in the update rule you will add with this g, that will be multiplied with g omega. So you can end it. So in this way, I mean, we can define this different kind of function, and so we can call all the functions here. So here we are calculating, so Euler step, oscillator. So here we have Tn, and then we have to give this input, so which will be all in, and then what are the, so what is the so f t x dt omega naught zeta. So x, now you have to define what you have to pass here, dt, then omega, and then you have to pass theta. So this is your Euler. So let me end it, and let me check if it is working, because after zeta maybe you have to close it. Okay, and let me run. Okay, so there is some error. Let me grab this. Euler. Euler state basically gives me output x next. So this is the x. Okay, so I have written down the code earlier. So let me check it. So let me just copy this function. And also, I mean, so there is also the code for this, how to compute the FFT also. So let me also copy it. And, okay, so let me just copy the whole code. And yeah, so I mean, there was some error. So I mean, if you look carefully, so we'll maybe we will able to fix that. So either so what the this problem, what this script is doing here. So basically here, I mean, this is the algorithm using Euler. So and this is the algorithm using Euler Maruyama, and this is the functional form. So you can include multiple terms. So I mean, if you have nonlinear system, then you can include here nonlinearity. So you can play with this function, and so this is your oscillator function, and this is the function to compute the FFT. This will give you the FFT result. So these are the functions, and here what you are doing. So basically you are plotting with time, and this is the response of the system. So this is the signal. This is the response that you are getting by using Euler method, and this is the response that you are getting by using the Euler-Maruyama method. So and also here we are computing the FFT of the Euler response, and we are also computing the FFT of the Euler-Maruyama. So now we can, and here we are plotting it. So let me run it and show the output. So here you can see that this blue one is from Euler, which is the deterministic equation using. So if you run it multiple times, so I mean you will not see change in this lookup. And the dashed one is from the Euler Maruyama. So that is why, I mean, if you run it multiple times, I mean you will see the change in the response. And here also in FFT, you can see, I mean, this blue one is from Euler and is from Euler Maruyama. So let me just uh, change the, so we can take it at 1, and let me run it. You can see that this is the system response. Now let me run it again, and you will see that it has been changed. Let me run it. Okay, so now you can see that there is a change in the system response, and also the response is changing, as we have demonstrated in the previous case. Because in each run, I mean, so since this is a stochastic system, so and I mean this is not an analytic function. So in each run, it will give you a different result. So and here you can try to play with, I mean, so this is I mean, so in this way you can do this using a second order differential equation. So you can try to extend it. I mean, you can play with different kinds of functions. So you can take a fifth order differential equation, and you can try to solve that, and I mean solve a stochastic fifth order differential equation, and you can play with the parameter values. Okay, so I mean, this is just the basic starting point of this Euler-Maruyama method. So I mean, this is simply I mean, you have a system where you have the where the noise term is additive, so you are not considering the multiplicative noise. Also, the noise is here Gaussian, so that means the mean value of the noise is 0 and it is delta correlated in time. So if you look at the response in the frequency domain, which you can try, so the in frequency domain it would have a flat spectrum. That means there is a not all the frequencies are present. So that is why it is a white noise. So with that, so I mean this is a Euler-Maruyama method, which is the modification of the Euler method, and it is accurate up to order H. So if you want to go into higher order, so I mean you have to have some kind of similar method of RK2, which you can try to develop. I mean, if you look at, I mean, so there are lots of books available on how to solve this stochastic differential equations. So you can search online and you can go through them. But I mean, so this is the starting point, and I mean, this is how I mean, this is just to get you the feeling of what a stochastic differential equation does to a system. So I mean, for each run you are having different kind of response, and I mean, the number of, I mean, if you keep on increasing the number of ensemble, then you can see the average behavior of the system, so that we will be able to observe. Okay, so with this, let me give you a summary. So what we have learned till today. So let me write down the brief summary. So first, we have learned about MATLAB environment. So we have been introduced to MATLAB. So we have looked at the, I mean, we have learned about how to save script and what is workspace, what is command window. So we have been familiarized with this MATLAB environment. Then we have been introduced with, I mean, array, matrices, and their operations. So we have learned that MATLAB is able to do very complex tasks, which I mean you have to write lines of I mean, so here, I mean, element wise operation is also easy, which you have to write, I mean, independent code if you are doing this in Python or C or C++. But in MATLAB there is lots of inbuilt function available which you can use. Then we have learned the basic of any programming or heart of any programming language, which is conditional statement. And then we have learned how we can do iterative tasks using MATLAB. So effectively this means use of loop. So where we have learned about for loop, while loop, and here we have learned about if else, and there is also if else if. Then we have learned about different kind of plotting in MATLAB. So in plotting, so we have learned about line plot and how to do a line plot in 2D, how to do a line plot in 3D. Then in 2D we have also bar plot, scatter plot, and also while learning FFT we have also learned about this stem plot. So these are all in 2D. So stem plot is basically a great way to visualize your data. I mean, so it, I mean, and also then we have learned about 3D plots. So we have learned about surface plot, mesh plot. Then we have a look at the difference between them. So there is a subtle difference between them. Then we have looked at contour plot, and there is also mm, in the last few lecture we have looked at this image SC plot. So image SC is nothing but you are looking at the surface part, but that is from the top angle. So this different kind of plotting we have explored. Then we have learned how to create or own custom function. So and also we have learned about how you can call function within function. So here calling function inside a local function. Then also we have learned about what is interpolation, how and there also we have learned the algorithm of linear interpolation. Then we have explored integration, differentiation, and after that so we have learned how to solve differential equations. Basically we have solved different kind of differential equation, for example first order, and we can solve up to nth order also. So any order of differential equation we have learned how to solve them. Then we have learned what is FFT. So and how FFT is different from DFT, and why it is useful. Then we have looked then we have done some calculation, or then we have explored this nonlinear oscillator system, nonlinear harmonic oscillator, which is your tapping oscillator system. So we have looked at the effect of nonlinearity in the system, and also in this here we have also discussed chaos, or how we can estimate Lyapunov exponent for harmonic oscillator or any kind of system. So this exponent for nth order differential equation. And then we have learned about what is SDE. So and what is the difference of it with ordinary differential equation? So here we have learned about what is additive noise. Also we have learned about multiplicative noise also, and but we mainly focused on this additive one. And here we have explored what is this equivalent of Euler, so which is our Euler Maruyama algorithm, and and we have implemented this in nth order differential equation. So implementation of Euler Maruyama algorithm in nth order stochastic differential equation. And in this context, we have uh, uh, we have also discussed how to simulate damped harmonic oscillator using Euler Maruyama algorithm. Okay, so these are the things that we have touched through in this course. I mean, so there are a lot of things maybe which I initially intended to cover but not able to cover. So, but the idea is that once you are fluent with the basics in MATLAB, then you can. So there is this law. I mean, this MATLAB help documentation portal available online, which you can search for any kind of. So suppose you. So there is this MATLAB help center. So here you will have all the documentation available here, or you can. So here you have documentation home. So you can go to MATLAB, and you can have every kind of thing. So mathematics, what is elementary math, you can go there. You can look for so maybe arithmetic operation, how to do the basic arithmetic operation. So what is the command for it, so how to write a complex number. So each of the things, so there are this example. So for example, this how to plot a complex number. So there is a code also available which you can go through. So there is a vast library of this documentation, and there is also functions. So this library is itself very huge. So the functions that are also saying, so what is plot function? It is a 2D line plot. What is this plot 3? It is 3D line plot. And we have also semi-log plot where x-axis is the log scale. So you can go through all. Also there is this contour plot. So if you want to look at the function of the contour plot, so this is a contour plot of matrix, and you can go through this. So the idea is that once you are fluent with your basics, and once you know how to think of, so the main thing is that how you can think of a problem. So if you are given with the problem, how you I can logically proceed with the problem. So that you have to master, and that you have to so similar to learning any kind of language. You have to learn it. So and the only way of learning is to practice it. So try to practice more and more in MATLAB, because this is a very useful tool to visualize or to analyze what you want to do with a system, or what you want to do with the data. So that you can easily do with MATLAB, because it has lots of inbuilt function. Not and it is very good with handling the matrix, with handling matrices. So that is why it is called MATLAB, which is matrix laboratory. So best of luck with coding. So code as much as you can, and I will uh, give a problem set. So where which you can try to solve, and which will uh, try to think how you can solve it. So basically you have to implement the logic, and you have to implement all the things that we have learned till today. So okay, so you can try to solve that, and I will upload that also. So okay, so that is the end for this course as of now. So thought of doing much more in the uh, you know, subject of regarding the non-linear dynamics part. I wanted to explore a little bit more, but yeah, so you can try to you can you can explore that on your own, so that will be the best. Okay, so see you.